What are we doing today? Polar slope and area. What's the homework tonight? In case you need a homework, check what you do. 564 multiplied by 5. Don't tell me you don't have homework tomorrow. Okay. All right, here we go. Kindly consider the following. Ready? What? We're doing slope and area, derivatives and integrals in polar notation. By the way, everything that you've done in rectilinear notation. What's that? Rectilinear notation. What's it saying? Cartesian, right? But what? X and Y, right? Can be done in polar notation in 2 dimensions. But you're going to find later on, this comes in handy when you go into 3 dimensions. Next year, Calc 3, everything you ever wanted to do in 3 dimensions, we're afraid to ask. Everything you wanted to do in Calc 1 and 2, Calc A, B, and BC, but in 3D, right? So multivariate or vector calculus next year, you're going to extend everything to 3 dimensions, and it's going to come in real handy to extend polar to spherical coordinates or cylindrical coordinates. So knowing polar is going to be important. Knowing vector is going to be important, especially if you're doing Calc 3 next year. All right. So this is just like a quick warm-up for next year, if you're taking Calc 3. The vector stuff and the polar stuff. All right, so kindly consider the following. 93 BC 4 says, find the volume enclosed by the polar graph r of theta is 2 sine 3 theta. Okay? That's the question. Watch, there's 2 questions. One was finding the area enclosed, and one was finding the slope at a point. Okay, so let's find the area enclosed. Alrighty? Let's see here. Who just came in? Ronnie and Eduardo. Okay. And Jared. Okay. All right, so this is a polar graph. Now, do you remember your polar stuff? Yeah. What kind of shape is that? Do you know? You know? You don't remember? Well, that's why God made calculators. So graph it. All right, so graph it. Here we go. Nope. I didn't bring up my calculator yet? Oh, time to bring up the calculator. Oh, my God. Where did it go?
Oh, we're in the sun, huh?
Yeah. All righty. So, let's see. That's Rotor, huh? That's Blako. So Liz and Shane and all this stuff. Oh, Liz is here? Alrighty. And Stephanie's good. Alrighty, so let's graph. Now, listen. It was, what the heck was it? 2 sine 3 theta, right? Okay. So let's make a new document. Let's make a graph. But I'm in F1 of X, in other words, function mode. So go to polar. How do you change it to polar mode? Menu, 3, 4. All right, just type it. Okay, and again, what the heck was it? It was 2 sine 3 theta, right? Okay, so 2 sine 3. Theta is down here. Right, the pi key. And that's it. Enter. Bing. And you get a 3-petaled rose. Excuse me, less talking, more paying attention, or you might want to go to the dean's office. I don't know. Alrighty. So you have a 3-petaled rose. The question is, what's the area bounded by those 3 petals? So how do you do integrals, in other words, in polar form? Now remember when we first did this? Riemann sums, right? Riemann rectangles. We sliced up the area into little rectangles, made the rectangles thinner and thinner and thinner, made the error smaller and smaller and smaller. But rectangles don't really make sense here because the edge is almost circular. So why don't we chop it up into a bunch of sectors? What? What's a sector? A piece of a circle. Let's see. Let's make a little circle. No, not there. Okay. Let's make a little circle. And let's take a piece of that circle from the center Let's make it from here to, say, here. So a slice of a pizza pie, let's say, is a sector. Right? Now, you know stuff about a sector of a circle, didn't you take geometry? When was geometry? 9th grade? Well, this is why you took geometry, for today. You spent all of 9th grade to do this today. Are you ready? Do you know anything about the relationship between r, theta, and s?
Yeah, S is R theta.
S equals, S equals r theta?
Yeah.
Yeah.
Yeah, R theta.
So that's like arc length, right?
Yeah.
But it's a specific arc length. It's a circular arc. Okay. All right. Do you know anything else about that sector? Do you know anything about the area of this piece of this pizza? The piece of this pizza called the sector of a circle. Do you know the area formula for this? Well, what's the area of a whole circle? Pi r squared. Okay. So I'm going to say that the area of that little piece is 1/2. Wake up. 1/2. My smartboard reboots every now and then. It's okay. R squared theta. Now it's lagging again. There you go. Does that make any sense? The whole circle is what area? Pi r squared. So if theta, what's theta got to be if you want the whole circle? 2 pi. So if you plug in 2 pi, what do you get? Pi r squared. What if you only wanted half the circle? How many radians is that? Pi. What if you plug in pi now? Does this make any sense?
Yeah.
All right, so that's the area of a sector or a slice of a circle. So why don't we talk about little infinitesimally thin sectors, little thin slices? Take these circular wedges and put them inside my polar graph and chop up the polar graph into very, very thin sectors. Why is that error prone? Where's the error there? Like in Riemann rectangles, there was an error. The top of the rectangle didn't match the shape of the curve necessarily, right? So why is this error prone? Where's the error here? Assuming that the edge of the curve that we're graphing, where did it go? The edge of the curve is circular, but it's not, right? But it's close. So if you make where did this come from? So if you make your sectors very infinitesimally thin, right? We're talking about, let's do it this way. Let's say delta A is 1/2 r squared delta theta. How about that? And let the delta theta get thinner and thinner and thinner and thinner and thinner and thinner and thinner, right? So that the edge of the circular wedge gets closer and closer and closer to the shape of the polar curve. It may not be a circle. It could be. Some polar curves are circles, right? All right, so how are we going to get this area then? Integral of this, right? Okay. So who's R? Well, it's given. Oh, this is easy. Okay. But what are the limits of integration? How much theta do you need, in other words? Is it always 2? It's not always 2 pi. Be careful because of the frequency. The 3 theta, the frequency may be, the period may not be 2 pi. All right, Valerie, you've got mail. Aurora, you've got mail. So, I want to do something like this. The integral, the area is going to be the integral of r squared d theta from theta 1 to theta 2, let's say. And don't forget the 1/2. Right? The area of that sector was 1/2 r squared theta. Okay. So, but r is 2 sine, okay, so squared, what do you get? 4 sine 3 theta, and 4 over 2. All right, so let's say we're going to do, all right, so let's do this. So say this is what we got to do. We're going to say 2, the integral, we got to figure out theta, of sine squared 3 theta d theta. Right, because we squared this, we got 4 divided by 2 is 2, we squared that, okay, perfect. Now, what are the limits of integration? All right, well, now let's go back to the graph. And let's just trace this thing. All right, so where's your trace? Menu.
Can you explain that?
Explain what?
Why you did 1/2 and then the r squared?
Because the 1/2 was here. This is the area of a sector. The half is part of the area of the sector.
Why are you taking the integral if that's the area of one?
That's the area of a circular piece. I don't have circular pieces. Plus, I'm adding up infinitely many little pieces. Just like we did with rectangles, right? Riemann rectangles. It's the same idea. So this is your Riemann statement. In the limit, as delta theta goes to 0, you get a d theta. You add up all the very thin d theta slices, and you get the total area. Okay. All right. So we're here. Now, so what are the limits of integration? Well, go to the graph and trace it. Let's see. Trace all. And let's see. So it's starting at. Let's see. Trace. Where's the trace? Why didn't it give me a trace? Did I hit the wrong thing? Dang it. Menu, trace, graph trace. All right, so where is it? It's at, why the heck is it starting there?
Yeah, I don't know.
That's weird. It's starting here. Usually it would start at 0, 0. Where did it start? 1, 1. Why is it starting at this random location? There you go. Okay. All right. So, that's really weird. See, I don't like this. I don't like it. Okay, there you go. 0, 0. All right. So it's here's 0, 0. Right. Now, how do I traverse the entire curve? I can go from. Notice the coordinates are r theta. So r is 0, theta is 0 radians, right? By the way, we should talk about that. What is a radian? Do you remember that? Remember, this is only true when theta is in radians. When is theta 1? What makes theta 1? If s and r are the same. So what if s is 1 foot and r is 1 foot? How do you get theta alone? Divide 1 foot into 1 foot and you get 1. What's the unit? They call it radians just because you feel like you gotta say something. But radians is not a unit. It's just 1, okay? So when you go to the graph and it says 0 radians, you could just say 0, right? It's just, it's 0. Okay. So starting at 0, 0, r is 0, and the theta is 0.
How did you get the trace? You had trace in which one?
I did number 1. Graph trace all or something, graph trace, something like that. All right, so now the thing is, what's your delta theta here? I just kept on tracing until I hit 0, 0. I eventually got there. All right, so if you keep, I don't like my delta theta. My delta theta is 0.3. Huh? 0.3 radians? That's not natural. The easy way to trace this is pi over 24. If your delta theta is pi over 24, when you trace it, you get pi over 24, you get 2 pi over 24, you get 3 pi over 24, you get 4 pi over 24, pi over 6. You get all the reference angles nice and easy, pi over 6. 5 pi over 4, 6 pi over 4. Pi over 24 is pi over 4, right? You get all the... I don't like this delta theta. Let's see. Menu. Probably window. Settings. See, where's my R? How do I manipulate R? I mean, theta. I want to manipulate x min, x max, y min, y max, and theta min, theta max, so I can get a theta scale. Right? Where the heck is it? Is it off down here? Is there something down here? No, there isn't. Huh. That's really strange. I not like it. Menu. Wait a minute. When you wrote the equation down, look at the theta step. That's rounded off, but that's approximately pi over 24. That's my theta step. Why is it not tracing with that theta step? Well, okay, how about this? Do you see that you got a complete graph?
Yeah.
From 0 radians to, what is this? 2 pi radians, so there you go. Now, if it's not a complete graph in 2 pi, you got to figure out what you need to get a complete graph. It's usually a multiple of 2 pi. Okay? So this one's easy. I would need the area from 0 to 2 pi. Do you see that it stops at 2 pi? All right, now I don't know why it's not tracing on pi over 24. That's about pi over 24. It's rounded off. It's tracing on, I think, did you see 0.3 radians? Not 0.13 radians? That's weird. It's weird. Anyway, let's not get stuck there. Let's complete the integral. So here we go. So now it's easy. It's from where to where? 0 to 2 pi. So,
Can you scroll up a little?
do it. How do I get 2 instead of a half? Well, because the function that we were squaring was 2 sine 3 theta. So when you square the 2, you get a 4. Right? So that's all. Okay, so how do you integrate this stuff? Now remember, we have a trig identity to make sine squared easy to integrate. Do you remember your trig identities? This is not new.
1 minus cosine.
Right, you got to know these trig identities. Let's see. What is it? Cosine squared theta is what? 1 plus cosine 2 theta all over 2. And sine squared theta is 1 minus cosine 2 theta over 2. But we have sine squared of 3 theta, so 6 theta. Do you see what we're doing? So sine squared of 3 theta is going to be replaced with 1 minus cosine of 6 theta all over 2. All right, let's go back. You got to know your trig identities. Did you see that sheet I put on Edmodo? All the stuff you need to know cold? Yeah, but did you see what I added? I added a bunch of trig identities. We should also add a bunch of stuff about arc length. I'm going to give you something about that maybe tomorrow. Okay? All right, so we're going to do this way. We're going to say 2 times. Okay, 2 times the integral from 0 to 2 pi. Wait, this is not right, though. I'm still not happy with this. I'm not happy with this graph. I don't think it's 0 to 2 pi. Wait, hang on. Let's go back to trace. I'm not happy with this trace. Okay, so, all right, so trace 1, right? All right, let's get back to, where's 0? Look what it's doing. God, really? Where's my 0, 0? I just had it. Where did it go? Just hit 0? Okay. All right, but now the trace, though, why is it going by 0.3, damn it? All right, so look, 0.3 radians, 0.6 radians, 0.9 radians, 1.2 radians, 1.5 radians, 1.8 radians, 2.1 radians, 2.4 radians, 3 radians, a little bit more than 3, whoops, back it up. Do you see that it was a little bit more than 3 radians to get there? So it's not 2 pi, it's pi. Okay. So the easy way to do this is to set this equal to 0. See when r is 0 again? It's going to be 0 at multiples of pi, not 2 pi. So that's how you're going to set up this integral. I don't like that setup. That's wrong. All right, so we said we're going to replace this with 1 minus the cosine of 6 theta all over 2. Let's break it up with this. Well, wait a minute. Can we factor out the 2, the 1/2? Factor out the 1/2. What do you got? 1/2 of 2? 1. Okay, that's easy. So integrate that.
Why do you have to skip so many steps?
Hmm?
You
I'm not skipping steps.
Because you
I'm just
already
simplifying.
erased it, and then I don't know.
In fact, let's make it even easier. Do you see that we're trying to find the area of 3 petals? But are these petals symmetric? Are each one of them a third of the total? So could you do this? Pi over 3. If you wanted, you don't have to. Get 1 petal and then triple it. You could. So, I don't know. What do you think? Is it easier just to go from 0 to pi or triple from 0 to pi over 3? I don't know. Either way. All right, you want to leave it? Okay, we'll do it. All right, so how do you integrate this? The integral of 1 d theta is theta. Okay. And the integral of cosine of u d theta? Who's, in other words, u sub. Who's u? Who's u? 6 theta. So who's du? 6 d theta. Okay. So you're going to replace d theta with du over 6. So minus sine of u over 6. There you go. And we're going to integrate that from 0 to pi.
Well, wait a second.
What happened?
You changed the balance on one, but not the other.
Oh, yeah.
Oh, this is true. You're right. You're right. Well, when you're right, you're right. Hang on. No, I didn't. No, I don't have to change the balance because I didn't write this in terms of u, actually. I went back to theta right away. Yeah, I did that on purpose and I forgot.
Integral of negative cosine, negative sines, shouldn't it be plus?
No, because remember how you check an antiderivative? If the derivative of the antiderivative is the integrand, you're good. The derivative of sine is cosine.
What? We're taking the integral.
I know, but how do you check an integral? Differentiate your answer, you should get that.
Yeah.
The
I was
derivative
gonna
of
say,
sine.
you
The
already
di-
have a minus there, so shouldn't it become plus?
no, the derivative of the SINE does not change the SIGN, does it? You got to say it careful.
Yeah.
The derivative of the sine doesn't change the sign, does it?
No.
So the antiderivative of the cosine doesn't change the sign. It's the antiderivative of the sine that changes the sign. Yes?
The
If you put
derivative-
cosine here, you're going to change sign, right? If you put sine here, you're not going to change sign. That's how you check, right? You differentiate your answer, you should get back what you started with. Okay. All right, so now it's easy. Just plug in stuff. Yes? All right, Anish, it's good that you're busy with something else. What? What thing? Oh, that's good. I'm going to do that. All right, so minus the sine of 6 pi all over 6 minus plug in 0. You got 0 minus the sine of 0. Well, that's very exciting. Over 6. Because the sine of 0 is 0. And notice it's not here anymore. All right, so anyway, this is all 0 over here. And what do you get? Well, what is the sine of 6 pi? 0. So pi minus 0 over 6 is pi. Okay, there you go. So the area of the 3 petals is pi square units. How's that? All right, well, that was just part A. That was part A. Are you ready for part B? Part B says, can you find dy dx along that curve at pi over 4? So, you still got the same curve. R equals 2 sine 3 theta.
How long will it do cosine,
Yeah, okay, that's the same graph. Now here's part B. Can you take this graph, right? And whenever theta is pi over 4, right? Pi over 4 is 45 degrees here. Can you find the slope of the tangent line there? So pi over 4 radians, right? Is 45 degrees. So if theta is 45 degrees, I'm at this point. Can you visualize the tangent line?
Yeah.
What kind of slope do you think that is? Give me an estimate. What do you think that number would be? The slope right here. What slope is that? This is a slope of 1, right?
Yeah.
What's that? Maybe about a half, right? All right, can you show that? That's the question. Okay. So, well, remember from vectors, how do you get dy dx? It's dy dt, well, it's theta today, over dx d theta. In other words, can you write y in terms of theta? Can you decompose this polar graph into an x and y component?
What is the question? What's
What's the slope of the tangent line along this curve when theta is pi over 4? So what's the slope when theta is pi over 4, 45 degrees, at this point right here? What's the slope of the tangent line right there? And I'm thinking it's looking like about a half, say, about. But how do you calculate it exactly, is the question. Well, you can use what you know about vectors. But now, do you remember something else? What is there a relationship between x, y, and theta?
Yeah.
what was it? X equals r cosine theta. So I want the derivative. I want the derivative with respect to theta of, well, x is r cosine theta. What's y? R sine theta, and r is so this turns into a vector product.
Oh my goodness.
Over what do you suppose?
Wait, why is that?
Just when we thought it was safe to have Dennis around, and Noel's here, and Cheyenne is here. Okay, what's that?
Why is this?
Why is what?
You did.
No, yesterday we said, or the last couple of days when we did vector notation, dy dx is dy dt over dx dt because of the chain rule? Okay. All right, so what is dy d theta? Well, you have to differentiate with respect to theta an expression for y. But y in polar mode is r sine theta.
You're ready. Take the derivative of
Take the
y.
derivative of that. Okay? So what am I going to write down here? Find the first derivative with respect to theta of 2 sine 3 theta times cosine theta. And guess what this is? It's just a lot of product rules, a lot of trig plugging in pi over 4. And let's do it. Are you ready?
It's cut off.
Why do you what?
No, you can't do that yet. You
On a calculator? You could if it's a calculator section, but what if it isn't?
can't.
Yeah, sometimes it isn't. Lately, the polar questions show up in part 2a. And the parametric question shows up in part 2a. And usually it's only one or the other. But sometimes it doesn't show up in part 2a. And sometimes there is a vector question and a polar question. That's rare on one exam. That's rare. But sometimes that happens. All right, so there you go. So how do you do this? Well, let's say, all right. How about we say this is the first and this is the second for your product rule? Y prime equals B prime plus U prime is a product rule. Well, how is the weather? Remember that song? That was a while ago. I just did it last week with the pre-calc, so I know it. All right. Anyway, so first times the root of the second plus second times the root of the first. Okay, so first times the derivative of the second, derivative of the sine, cosine. Okay. All right, plus the second times the derivative of the first. How do you do 2 sine u? Chain rule, right? Right. So it's sine. Derivative sine of stuff is. Derivative of sine of stuff is cosine of stuff times the derivative of the stuff, which is 3, but you had a 2, so 6. Okay. Does that sound right? Okay. Over.
It's like roast thing.
All right, let's do it again on the bottom. Let's make this first and this second when we're doing the product rule. So first times the derivative of the second is negative sign, right? Plus second times the derivative of the first, but the derivative of the first is still 6 cosine 3 theta, isn't it?
Yeah.
Okay. And you can simplify that or whatnot. What happened? Did I do something weird? Okay. All right, so that is your statement for the slope of the tangent line anywhere along that polar curve, but they wanted it pi over 4, so what do? Plug it in, right. So what's dy dx at theta equals pi over 4, or with key, right? Well, okay, what is the sine of 3 pi over 4?
That's 135 degrees.
Pi over 4
What is
is
this
45
thing?
degrees, so 45, 90, 135. What's the sine? I took it away on purpose.
This
What's the
would be-
sine of 3 pi over 4? What?
This would be
Oh,
calculated
right, so-
section.
This could be a non-calculated section. You should know your reference angles, sine, cosine, and tangent of pi over 4, pi over 3, pi over 6, any quadrant.
Oh, 3 pi.
All right, so pi over 4, pi over 2 pi over 4, 3 pi over 4. You're in the second quadrant. The signs are positive, and it's based on 45 degrees. So what do you say?
Right, 2 over 2.
Isn't it rad 2 over 2? Yeah, okay, times 2. So this part is rad 2. Okay. What's the cosine of pi over 4? No, just pi over 4. This is 3 pi over, this is 3 pi over 4, but this is just pi over 4. So the cosine of pi over 4 is just, it's rad 2 over 2. Right? Same thing. Plus, and that's just 1. I can don't do everything in one step, I mean, Aurora's upset already. So don't skip steps. What's the sine of pi over 4? Rad 2 over 2. This can happen on a non-calculator active section. Be careful. You got to know this stuff. And what's the cosine of 3 pi over 4? Well, again, pi over 4, 2 pi over 4, 3 pi over 4. Second quadrant cosine is negative based on pi over 4 is rad 2 over 2, so negative rad 2 over 2. But don't forget the 6's in here. Okay. Over. Oh, God. And all of this is supposed to be a half? We guessed a half, right? You think this is going to be a half? I don't know. All right, and then this is the same. 2 sine 3 theta is still going to be...
So, why didn't we make that one negative? That close.
What the frac did I do?
That's right too.
Is it rad 2?
Right.
Wait, what did I do?
Yeah, that's right. But
This is rad 2 over 2. Where did I get the rad 2?
because rad 2 over 2 times 2 is
Okay, we simplified this whole thing, right? Oh, okay. It's 2 times 2 rad 2 is rad 2, right? Yeah. 2 times rad 2 over 2 is just rad 2. Yeah, that's right, that's right. So this whole thing, well, it's different. I can't do that. All right. What is the sine of 3 pi over 2?
Wait, but shouldn't that be negative? Because
This one's going to be negative.
no, at the top.
The sine is positive in the second quadrant.
then
The
what about
cosine is negative.
So shouldn't that a whole thing?
Yeah, but we're not in the third quadrant. We're back in the first. This is 3 pi over 4. This is just pi over 4. Right? So that's okay. Don't. All right, let's not second guess the first sign. It's done. Yeah, you got to know that.
It's the new Bible.
But you got to know more. I'm going to write another.
The newest testament.
I'm going to write another page. Okay. Right. There should be another page on the trig identities you need to know and the arclength formulas you need to know. Is there an arclength thing in there?
It's typed by Garcia. You don't have a first name though, right?
Did I type that on? I didn't write that.
No, it,
That's Sean Bird.
It will say.
Okay, remember Sean Bird? The very first day of school, we did a primer about the Inspire. That was by Sean Bird. It was the same guy. Anyway, so what's the sine of 3 pi over 4? It's rad 2 over 2 times 2 is rad 2. What's the sine of pi over 4? Rad 2 over 2, but I want it to be negative now. Okay. What's the cosine of pi over 4? Rad 2 over 2 times 6. And what's the cosine of 3 pi over 4? Isn't that the same thing? Negative rad 2 over 2. Holy God, what a mess. Okay, so rad 2 times rad 2 is 2 over 2 is 1 plus. Okay, rad 2 over 2 times negative rad 2 over 2 is what? Negative. What's rad 2 over 2 times negative rad 2 over 2?
No, it's 2 over first negative a half.
Rad 2 times rad 2 is 2, and 2 times 2 is 4, so negative 2 over 4 is negative a half, right?
But then times 6.
Times a 6, so negative 3. That's the top, right? All of that just for negative 2. Okay. This is going to be what? Negative 1. Okay. Now, how is this different? Is it? No, it's still a negative 3, right? You guessed wisely, didn't you? Amazing. All right. Now, there's only one more thing left to talk about. It's arc length in polar form. Let's talk about arc length in polar form. Okay, just one little thing. That's not part of this question. I'm just gonna one little thing. So we did slope. We did area. Now arc length. Okay. Now think of arc length this way. Sort of like parametric mode. What was parametric? D x d t squared plus dy dt squared dt. Well, how about this? dx d theta squared, like we just did to do the, like a parametric slope? Well, yeah, that would be 0. Okay. Plus, dang it. There you go. But how to get dx d theta? Just like we did. You know how to get dx d theta? Like this. Okay. Alrighty. So, all right. So let's write in general what that is. If x is r cosine theta, well, let's make a point of this. Is r constant? No, it's that polar curve. It's changing. R is changing. Its theta changes. So let's make a point of saying that it's not like r is a constant. It's a function in theta, right? Okay, so you need x. You need x prime. There's x, and you need y prime. There's y. So do like we just did with the slope, right? Differentiate r theta cosine theta. We had a particular r theta, right? Well, I'm doing this in general right now. It's separate. It's not the same question. Separate question. Okay. And then y is r of theta times sine of theta. So what is x prime? So it's r prime. I'm going to abbreviate. R prime times first times the root of the second, right? Plus the second times the root of the first, which is second. Wait, first. You're doing it. I don't do it that way. I do it in the other order. Sorry. Yeah, you're doing it right, but I'm doing it in the other order. I can't remember it that way. All right, first times the root of the second. I'm abbreviating. I'm not writing a lot of thetas and a lot of parentheses, right? First times the root of the second plus the second times the derivative of the first. Okay. What's y prime with respect to theta? First times the derivative of the second is, what's the derivative of the sine? Cosine. Cosine theta. So first times the derivative of the second plus the second, which is sine, times the derivative of the first. Okay. So there's your x prime, there's your y prime. Then you got to square them. Square it, add it, square it. Okay, are you ready? This is, by the way, do you know Steve Dolsky?
Yes.
He created that. Do you know the song Technologic by Daft Punk?
Yeah.
Technologic,
Yeah.
right? Well, he did a song based on that. He was like, square it, add it, square it. And when we did vectors and magnitude of vectors, yeah. So anyway, so square this, add them up, square root them, integrate it, and have fun. That's it. Okay? So you get, oh God, you get the integral from theta 1 to theta 2 of this guy squared. How am I going to write this? I'm going to write it this way. I'm going to write this backwards. This is negative. I'm going to put this in front. R prime cosine theta minus r sine theta, square it, plus, okay, this guy, I'm going to write r prime first. R prime sine theta plus r cosine theta, square it, add it, squared it, integrate it, and now, we got 1 minute left? Okay. Exercise left to the reader. This simplifies to something insanely easy. Are you ready? It simplifies to this. I don't have the time, but you can do it. You can simplify this. Do it, okay? It simplifies to r prime squared plus r squared. So that's a new arc length formula. So you could do it like, do all of this mess if you want, or start here. It saves a lot of work. Okay? So you can always just do this. What we did. Okay. Just do that. But it always boils down to this eventually. So why not start here? All right. So I'm going to write an addendum to Sean Bird's page. All the trig identities and all the arc length formulas, including this one. Okay. And that's the stuff you should know cold for BC and AB. Right? Yeah.
Are you gonna, when you write, you're gonna make it all like
It's going to be 4 pages. It's going to be that double-sided. It's going to be this double-sided.
okay, but you're gonna remove the old one also?
Yeah. I might even just print it out and give it out tomorrow. Yeah. Okay? All right, that's it. So what are we doing tomorrow? Just like yesterday. What are we doing tomorrow? Practice FRQs on Polish stuff. Nothing new tomorrow. You are done. This is it. BC. It's finito. Finito. It's over. No more calculus. Nada, ningún diente.
Wait, you just said no more calculus.
No more calculus until next year.
Oh, we have calculus after this.
Oh yeah, the CD calculus. Wait until you see CD calculus at the DAP. That's our movie marathon, The Hobbit. All right.
Game day.
Computers first around.
It is?
Yeah, I opened up this and then I don't know, I tried to like minimize it and then screw it.
Get to that in a minute. They want me in the hallway for 2 seconds. I gotta move. All right, wait. Okay, you two. That's it. BC's over. A little review tomorrow. And that's it. Have a nice summer. Have a nice AP exam.